This is one of the properties of the determinants. This simply tells us that the determinant of an inverse of a certain matrix, if inverse is possible or the matrix is invertible, is just equal to the reciprocal of the determinant of the matrix A itself. So we are going to show that this equivalence is true so that later in your respective classes or respective concerns, if you are solving for the determinant of an inverse and you don't know what the inverse is yet, then you can just simply take the reciprocal of the determinant of the matrix A itself. To be guided with this, we're just going to use here a certain matrix in the form of a 2 by 2 matrix. Okay, so let's just simply use 2 by 2 matrix. I know that this property could hold to a general form of matrix, but to just show a proof of this, let's just simply use a 2 by 2 matrix here. And if you're going to have matrix A, okay, matrix A, something like this, let us simply use these components. Let's have A11, A12, then you have A21 and A22 for us to have a 2 by 2 matrix here. Okay, now since we're trying to show that the determinant of the inverse is equal to this, of course you can automatically get the determinant of A here because we have the shortcut. It is also the reason why we are using 2 by 2 because we have a formula for the determinant of a matrix A using these components. The result here is the product of the diagonal here, the product of A11 and A22 less the other diagonal A12 and A21. This is the determinant of this matrix A. Okay, so later we're going to connect it with this as soon as we were able to get the inverse of A. So let's start first with the inverse of A. Now, inverse of matrix A actually has a specific formula. Okay, the specific formula for the matrix of A is this: 1 over the determinant of A, okay, which is actually this one here. Take note of that. Times, we have this notation. Okay, we simply try to interchange the diagonals. You have here A22, and then you have A11, and the other diagonal will become negative, A12 and A21. Okay, so negative, sorry, that's a negative here. In short, if we are going to plug in the determinant here, you're just going to have 1 over this result. So let me use some space here. The product of A11 and A22 minus A12 and A21 to be multiplied with, again, this, because to solve for the, what do you call this one, the inverse, we're going to do it like this for 2 by 2 matrix. Okay, so you will have here A22 minus A12 minus A21 and A11 here. So when you multiply that, you will get the inverse equal to this set of expression, A22 over this A11, A22 minus A12, A21, and you have here minus A12, denominator same, A11, A22, A12, and A21. Of course, for your next row, you have minus A21. You will have here A11, A22, A12, and A21. And finally, you have here A11. You have A11, A22, A12, and A21. This is the inverse of matrix A. Now, let's try to solve the determinant of this. If this is equal to the reciprocal of this. So let's try. So the determinant of the inverse, okay, you have like something like that, is equal to, using the formula, you're going to multiply this. You will have here the result, A22 over A11, A22 minus A12, A21, 21, to be multiplied with this A11 over A11, A22, minus A12, A21. That's for this diagonal. Less this diagonal here, you have negative A12 over the same denominator, A11, A22, A12, A21, okay, times, you have this, A21, A11, A22, minus A12, and A21, okay? So, continue, multiply the numerators, you have A11, A22, just simply arranging them, so that we can look for relationships on their denominators, A12, A21, minus, that's negative times negative, so that becomes positive, positive A12, A21, all over, you will have A11, A22, minus A12, and then you will have A21, okay? So after this, simply try to look at their denominators, okay? Sorry, forgot to mention this is actually the square because you're multiplying, okay? You're multiplying, take note of that. You're multiplying them, so you're also going to multiply this as well as that. So this should be squared and squared. I forgot to write that. So continue. Your numerator will just become, since we have the same denominators here, so you can simply combine them into one. You have A11, A22, minus A12, A21 over, again, this is what I forgot earlier, the square of this. Because again, earlier it was multiplication. Now look at the numerator and denominator. They are of the same expression. They are just the same expression here. So as one, you can cancel. You can cancel one of the two here. So what you have now is just simply 1 over A11, A22, minus A12, and then A21. Because again, this has two of that. Two binomial expressions on this form, A11, A22, A12, and A21, okay? Once you cancel this and that, what remains here is 1 still on the numerator, and the numerator becomes, denominator I mean, and then the numerator becomes 1 alone. This is the determinant of your A inverse. And what was the relationship that we're trying to look earlier? What is this? Okay, what is this? This is just simply, okay, the determinant of A as shown earlier. A11, A22, minus A12, A21. That's just that. In short, we can establish now that the determinant of A inverse is just equal to the reciprocal of the determinant of A. This shows this property of determinants. Okay? So with all of this already taken down, this shows that the determinant of A inverse, even if you don't know what inverse is, you simply take the reciprocal of the determinant of A for that result. This is properties, laws, and theorems. Please subscribe now.